Hello everyone. Today we start our new lecture series on earthquake resistant construction and design, and today's topic is seismic lateral force analysis. We have to find seismic lateral force analysis of a building. So first we have to find the whole building load and then we distribute this load as a floor wise. So for that we have two methods. One is the equivalent static force analysis and second is the dynamic analysis. In today's lecture, we will discuss about the equivalent static force analysis. So there are some assumptions which we use in the static force analysis. First is the assume the structure is rigid. Second, assume perfect fixity between structure and foundation. Third, during ground motion, every point on the structure experience same acceleration. Fourth, dominant effect of earthquake is equivalent to horizontal force of varying magnitude over the height. And fifth, approximately determine the total horizontal force base shear on the structures. Or there are some limitations also we will discuss like this. The limitations are in the equivalent static force procedure, empirical relationships are used to specify the dynamic inertial force as static forces. These empirical formulas do not explicitly account for the dynamic characteristics of the particular structure being designed or analyzed. These formulas were developed to approximately represent the dynamic behavior of what are called regular structures. Structure which have a reasonably uniform distribution of mass and stiffness is called the regular structure. And last is the structure that are classified as irregular violate the assumption on which the empirical formula used in the equivalent static force procedure. Here irregular means there is not a non-uniform distribution of mass and stiffness. So here we discuss how we find the base shear of the building and how we distribute this base shear on the different floors. For that we have to first find the base shear, and the formula of base shear is Ah into W, and A is equal to Z by 2 is equal to I by R is equal to SA over G. So there are different steps we have to involve for finding the base shear, and after that we have to distribute as a height of the building. So here are the steps of this finding the base shear. First step is first we have to find the zone factor. So zone factor is depend on the city. For example, if we live in Jhalawad, so Jhalawad is come in the zone 2 because here earthquake is very rare. That's why we are in zone 2, and for zone 2 here value is 0.10. If you not know our city is found in which zone, so here in 1893-2002 give annexer. In annexer they give the zone and as well as the zone factor values. So these are the annexer which we found in IS 1893-2002. Here are different cities with zone and zone factor. So you have to find zone factor. After that you have to find the importance or weight. So because our formula is Ah into W, so we required weight also. So here are the clause where we found how we find the seismic weight of floors and seismic weight of buildings. So these are the clauses which we involve in finding the weight of the floors, and these are clauses found in the IS code 1893. These are our third step, compute the natural period of the buildings. So TA is required for finding the SA over G value or spatial acceleration value. For that first we have to find the TA, and TA is equal to 0.075 h की power 0.75 for RC frame building and 0.85 h की power 0.75 for steel frame building. Here in clause 7.6.2 there one formula is also given here, but this formula is given for the infill panel. When in our structure infill panel is given, at that time we have to use this formula. Here one thing is missing. In this formula you have to write 0.09 h. Here h is missing. You have to write here h divided by root d. After finding the t value, you have to find the SA over g value with the help of this values or this graph. In our question, soil criteria is already given. Our soil is hard soil, medium soil, or soft soil. You find SA over G value either from this diagram or you have to find with the help of this formula. For example, if our value is 0.12, so our T value is 0.12 and this lies between this, and our rock is hard. So we have to take SA over G value is 2.50. So with the help of this diagram or with the help of this value, we have to find the SA over G value. So we have to find Z and we have to find SA over G value. Now our remaining part is I upon R. So I is the importance factor. Importance factor means your building is how much important. So for important buildings or important services, we have to take I value is 1.5, and for other buildings we have to take I value is 1. After that, we have to find R. R is the response reduction factor, and it is depends on ordinary RC moment and special RC moment. For ordinary RC moment, we have to take 3, and for special RC moment, we have to take 5. If you have not given anything like ordinary RC moment or special RC moment in our question, then you simply take the special RC moment resisting frame, and the value for that is the 5. After finding this, you have get the AH value, and simply you have to multiply AH into W and you get the base shear. So this is the AH value, and with the help of this value and with this value we have to multiply with W and we get the base shear. After getting the base shear, we have used this formula for distributing the load. For example, if you have a 3-story building, so 3-story building and the height of 3-story building is 3 meter, and total mass of first floor is 2000, second floor is 2000, and third floor is 1500. So simply you have to put the value of WIHI square, means here we put the first floor value. So for first floor, here W is the 2000, H is the 3, so 3 meter square, or is the summation of 3 floors, and VB we already calculate. So simply we have to multiply VB with this value and we simply get the values of lateral force on each floor. So this is the criteria which we used for solving the base shear and distribute the base shear on a different floor. Thank you.